Well, good morning, everybody. It's a great pleasure for me to announce this morning's plenary talk that will be given by Luke Olson. Luke is a professor in the Department of Computer Science at the University of Illinois at Urbana-Champaign, where he's also the director of computational science and engineering. He serves as an associate editor for CISC and co-chairs the biannual meeting on multi-grid methods in Copper Mountain. He works on design, analysis, and implementation of high-performance multi-grid methods, and he has developed numerous software packages, for instance, a PyAMG, Raptor, or Setter. And today he will talk about methods and models for reducing communication, and I'm looking forward to this talk. Welcome, Luke.
Thank you. All right, the Saturday crowd. Thank you for having me here. The title will need some explanation because it's a bit big. Methods and models for reducing communication. It's going to be a little bit more precise than that. I want to acknowledge my collaborators on this, Shelby Lockhart, Bill Gropp, and really the mastermind behind all of this, Amanda Benz, and Andrew Reisner, who's now at Los Alamos. All right, so what's this talk actually about? It is about methods and models to reduce communication, but this really isn't a new problem. In fact, everybody's doing this. And there's a lot of work in this area. What I'm going to focus on here are some sparse matrices, and at the end, some collectives. And I'm going to try to highlight some ways of organizing communication and some new ways to model what's happening and what's going on in these kernels. This is probably unnecessary. Sparse matrix operations come up in a lot of settings from our code in our PSAP center at Illinois, modeling plasmas, have Paul Fisher's NEC 5000 simulations. We solve eigenvalue problems. We solve large sparse linear systems coming from physics, coming from data, coming from graphs. I just did a little grep on PP20 abstracts, and they do show up a lot in the abstracts, sparse and communication. So we're going to focus much of our effort on this one, the sparse matrix vector multiply, and I'm going to motivate why we're looking at that problem that's been looked at quite a bit. So who cares? Well, these SPIMVs come up a lot. If we just take a preconditioned CG iteration, there's a lot going on here. We could focus on this first step with the inner product, but the sparse matrix vector multiplies, the SPIMVs, are going to show up a lot in these two red lines, especially if we're using something like multigrid. We might incur tens, hundreds, thousands of sparse matrix vector multiplies to solve a particular problem. And the sparse matrix vector multiply is going to be a limiting factor in this case. So let's take a look at this, an anatomy of a sparse matrix vector multiply. Took a sparse matrix, and in this case, I partitioned the matrix row-wise into 4 processors, and I've colored and highlighted each one of the entries in the sparse matrix in 2 ways. Dots that are solid are ones where all of the computation associated with that would be on processor. The ones that are outlined on the side here require communication of the vector data. Okay, so on the left, kind of distinguished these colors of where the data lives. It's a row-wise on each processor. And on this one, I've colored it in terms of where the data is sent. Okay. So when we execute this SPIMV, we're using point-to-point communication. And this is fundamentally different than using collectives. And so in this slide, I'm giving a kind kind of a processor mapping of who's communicating. And in the middle, I've taken one sparse matrix and 8,000 processors and just labeled the communicating cores or communicating processes that are part of this BIMV. In contrast, there's an all-reduced collective on the far left, using recursive doubling in this case, and we can see that the involvement of processors is much different. Moreover, if we do a strong scaling case, this BIMV becomes more and more dominated by communication. Okay? There's a great paper by Ben Nunn and Hoeffler on collectives in a deep learning setting, and it's a great read. All right, so now we're getting more to the point, and we're going to see kind of the main challenge that we've been looking at, which is in algebraic multigrid. Algebraic multigrid attempts to solve systems AX equals B through a series or hierarchy of successively smaller problems. And the advantage of having smaller problems is that they should be cheaper, and they're not, which is the issue. Just a schematic of what's going to happen. We'll look at this in two different ways. Here I took a grid on the left and Poisson problem, and we can see the sparsity pattern of the matrix A. If we go to one course level down, the problem, it is smaller, and we can see that the sparsity pattern is starting to grow a little bit. In fact, if we go down to another coarser level, we have much fewer points and a much different pattern in our matrix. So while on one hand, on the fine level, the original problem, our sparse matrix looks fairly regular and even almost structured, by the end we have a much different pattern. And this is going to be one of the complicated features of these types of sparse matrix vector multiplies. Constructing an algebraic multigrid solver requires a sparse matrix multiply as well, two of them, and also several sparse matrix vector multiplies. We'll look at the setup phase a little bit. And then applying the solver is all SPIMVs. So here's roughly what this looks like. We've seen a Vcycle, and I've painted in blue here the matrices on each case. And the notable feature here is that the problem gets smaller, but the number of non-zeros per row starts to grow relative to the size of the problem. Okay. So here's the main issue. I took a linear elasticity problem from MFEM and 16,000 cores, and there's 19 levels in that multigrid hierarchy. On the left was that original picture with the fine level matrix. It's very structured, has a nice tight pattern to it. On the far right, when we're down at some of the lower levels in the hierarchy, we have a much smaller problem, but it has a much wider sparsity pattern. And you can see what happens here. That's not what we want, right? We wanted successively smaller and smaller problems so that they were cheaper. And this is the core problem that we're going to address. Okay, let's to move that down. Here's a different view. This one's just on a Laplacian. It happens all the time on these types of problems. Here I've a slightly smaller problem, and there's 9 levels in the hierarchy. On the left, distinguished the setup and the solve time on the right, and also highlighted the different portions. So there's computation, and there's vector communication, which we would see in a sparse matrix vector multiply, and then there's matrix communication, which we would see in a sparse matrix multiply, in forming the multigrid hierarchy. And you can see in each one of these cases, the communication starts to dominate, especially at lower levels in the multigrid hierarchy. So what we want to do is we want to understand what's happening and potentially how to design new communication algorithms that can address this. So there's lots and lots of ways to handle this, and this would be quite a task to give a full overview. There are algorithms, of course, that can be constructed so that they incur less communication penalty. I've taken a sample of just some just nice gems of articles and kind of put them up here, but it's not exhaustive. There are ways of removing data. So in AMG or an algebraic multigrid, there are approaches where we can simply set up multigrid hierarchies so that they communicate less. There's a really great paper on reducing complexity in parallel AMG. There are other ones where you can just remove the non-zeros in a systematic way. And then, of course, there's different layouts. We can think of them in multiple different ways, either restructuring the matrix itself or redistributing parts of the data, especially at lower levels of the multigrid hierarchy. And of course, there's different ways of handling the sparse matrix operations. I showed you a 1D partition of the matrix. There are many ways of doing this. There's an excellent article by Bowman and Wolf on doing some different types of partitionings and some more recent works as well. And then there's traffic. So given a particular algorithm, there's a bunch of communication. How do we handle that type of traffic in the network in a sensible way? There's ways of, like the title, so I posted that one twice, overlapping communication with communication. That's a nice article. There's ways of doing task mapping and processor mappings in systematic ways. I'm going to be talking a lot about that last one, and it's our node-aware approach to doing this communication. So we would like to recognize the limits, what's contributing to the communication limitations, and some opportunities in the machine hierarchy in order to address them. All right, let's look at a couple of observations. And these are straightforward observations. One of them is we're just sending a lot of messages. That's not a big surprise. So on the left, the same problem, printing out the maximum number of messages, and on the right, the maximum size of the messages. So we send more messages, we send larger messages, both of those are going to contribute to the overall communication cost. Okay, not a big surprise. Let's look at a couple of models, though, and see if we can understand or try to peel apart what's happening in this particular case or for these types of problems. We're going to do a ping pong test in a number of these modeling plots where we take on one node a certain number of processors, and we send data to processors an equal number on a different node. And then they come back and we time that. And that's a ping pong or a high volume ping pong if we're sending lots and lots of messages. And a typical model for this is to use something called the postal model or the alpha beta model, where we have the latency and the inverse bandwidth. And on the right, I increase the number of bytes that are communicated in that ping pong test. And in each one of the dots, I increase the number of communicating cores. And so at the end, this one's on blue waters. There's 16 processes on one node communicating with 16 on another. And we even marched the nodes out further and further to get more and more dots. And we can see that the alpha beta or postal model has trouble picking up all of the features in that ping pong test. So there are ways to make this a bit more accurate. This one is called a max rate model, where we can incorporate an injection limit. Okay, we've seen this in other types of models like the log P model. And in this one, we can take and penalize what happens if we get to more and more communicating cores. And so I took the same plot here, and in the orange is where less than 4 communicating cores are used in the ping pong. And this max rate works well. In fact, it goes back to the alpha beta model because there's no injection limit. And then if we penalize the injection limit, we start seeing that it hits the rates for, in this case, I drew the curve for 16 processors per node. So the cost depends on the number of communicating processes, all right? Also not a big surprise. Let's go to another model then, too. We can take and extend that, this max write model, to all kinds of different levels in the machine. And so in this one, there's more than 4 communicating processors. There's less than 4. There's even communicating on node, just between processors on node, or we can even drop that down to on socket. And the other non-surprise is that on-node communication is cheaper than off-node. In fact, it can be quite a bit cheaper. And if we extend that all the way down to socket level, communication on socket is cheaper than on-node. So we're going to try to take some of these observations and pull them into a way to organize some of the communication in the sparse matrix vector multiply. But our modeling isn't, it's not going to catch everything, okay? So even with the max rate model with the penalty for injection, there's other stuff going on in the sparse matrix vector multiply. In fact, this came up, we started doing this work 4 years ago at the SIAM PP in Paris from a lot of the discussions there. So it's been quite helpful. Here's one of the kind of corner observations, so observation 3. Here we're going to do a high volume ping pong. So we send lots and lots of messages, and we increase the number of bytes being sent. One of the things that we've observed is that the post order of the receive has a big impact on the time. And so there's an iReceive order and there's an actual order. And if those are all in sync, there's no search that's needed and you get to pick up the pieces in the queue right away. Or it can be completely unordered and you have to search through the whole queue and find the tag that you need, and the model can be quite a bit off. Okay. So here on the left, I have a best case scenario where we've ordered things perfectly and the max rate model fits for high numbers of messages and over a range of message sizes. On the left, we've reversed that queue order or the receive order, and we can see what can happen in the worst case. It can be up to a couple of order of magnitude off in the model compared to the timings that we see in practice. So to compensate for this, we can add a term to our model. And in this test, we take and penalize with an n squared term, where n is the number of messages in that queue. The other issue that we'll see is when we have lots of messages and lots of large messages in the network, that there's opportunity for congestion in the network. And modeling point-to-point contention it's very difficult. So we lined up a problem where we literally lined up a problem where we took 4 nodes and we start sending high volumes of messages between those nodes in a line. This is on blue waters where we can fix that setup. And we notice that when we do that, we're missing a huge part of the model, especially at very large message sizes. Okay, so just to reflect on this, we're doing a high volume ping pong down a series of nodes, and the max rate model is unable to pick up or model the communication behavior, and we think it's because of contention, because we have a small problem for that. So what we'd like to do in general is to figure out how do we penalize the model so that if there's a message going from one node to another node, that we can model or account for some type of contention. And the way that we're going to do this is that we're going to model it with a penalty for waiting in a network link and the number of bytes that it's going to take to traverse a link. To gather that data, we make an assumption. We make an assumption that we're on a cube, and we have a message distance on that cube. And then there's an average number of hops and an average number of bytes, and we get a value for our ping pong test, and we include that in our model. Okay, so just to unwrap a little bit, we have a max rate model that penalizes for injection. We have a term for a queue search, which will penalize for post orders. And we have a penalty term for contention, which assumes that we're going to run into a certain number of bytes or penalties on a length of a certain length. Okay. Let's see what that does. So here on the left, I took our multi-grid hierarchy for elasticity again, a much smaller problem to test. And on the left, these are the sparse matrix vector multiplies. And on the right, this is the AP part of forming the coarse grid operator. So sparse matrix A times sparse matrix P to form P transpose AP. And we can see what happens pretty clearly. If we just include the max rate model, and this was the bothersome part, just the green lines were not accounting for all of the communication costs in the sparse matrix multiply, especially at lower levels in the hierarchy. And the matter of contention pops up even more when we have sparse matrix times sparse matrix. In that case, we're sending much more data. We're sending whole rows of the sparse matrix in the computation, and we see contention taking over. Okay, so the model's improved with the queue search time and contention parameters, and those times tend to dominate on coarse levels. So those are our key takeaways. That it's cheaper if you do communication more locally, okay? High message counts incur a queue search cost. Large messages and high message counts lead to network contention. Okay, there's really no surprises here, but what it does say is that we need to reduce the internode communication. Seeing if we're paying attention. Internode communication. So how are we going to do that? We're going to go back to our matrix, and instead of thinking about just the processor layout for that matrix, we're going to imbue the node layout too. So here we took the same matrix, and now we color it in 3 different ways. We have entries that are going to do work that's all local to the processor. Those are solid. Then we have ones that only need to communicate vector entries with other processors on node. So between 0 and 1, those are going to be on the same node. And then we have ones that are outlined here that are going to be off node. Okay. All right, so here's a schematic of what's going on with the standard communication. We're going to communicate values between node N and node M from different processors, in this case 4. And we can see that there's a high number of messages that can go between 2 nodes. That's the contributing factor. We also notice what happens in particular to process P trying to send to node M is that it can send duplicated messages if it's sending to process Q, process S, process T, etc. So there's an opportunity that if there's a single message that needs to be sent to node M, just do it once instead of duplicating that data. And so here's something we term 3-step communication, because it has 3 steps. One is that actually it has 4. The 0th step is that you can do communication on node. After that, we're going to do some off-node communication. So on that off-node communication, we're going to gather the things that need to go to node M. We're going to communicate them to node M, and then we're going to give everybody their information on node M. And so now we've kind of checked some boxes. We've reduced the number of times we're sending stuff over to node M at a cost of doing stuff that's more local. So this takes more work over here, doing the gather and the scatter. And so hopefully there's a payoff, and there is. So this is a case of our linear elasticity from before. And on the left, these are the maximum number of messages sent from any process. And we can see that the trade-off worked. So the number of messages that we're sending off node drops dramatically because we're not sending all of those duplicate messages, and we're sending just a fewer number. But it increases the number of messages that we're sending on node due to that gather and the scatter. Okay, that's good. It also says that the maximum size of the messages goes down off node, and that the maximum size for any process goes up on node. Okay, that's also good. And in total, the total time goes down dramatically. So that's a very good thing. So here on the left, we did the total time, and on the right, we can see that it just helps extend the strong scaling limit for these types of problems. So this is modeling and showing the performance for a sparse matrix vector multiply, but things aren't so rosy when we start thinking about the setup phase, which is often ignored in algebraic multigrid. In the setup phase, we're again responsible for doing P transpose AP, but in this case, we're going to have a much higher number of messages, and collectively, we're going to have a large volume of data that's being sent, even in the three-step communication case. And so we can go back to the model and think about what's going on. In this case, we're doing this ping-pong test again of a single message between 1, 4, and 16 communicating processes. And here I've taken the max rate model for each one of those cases. And there's different routines being used depending on the message size. So rendezvous or eager or short. And so our goal is to minimize the number and size of the internode messages, plus we'd like to have each process send equal portions. Okay? So when we have the sparse matrix multiply, we have too many messages and they're too big and they're not balanced between the communicating cores on node M versus node N. And so we're not going to do that anymore, that big step in the middle. We're going to do slightly different, and this one is a two-step method, because there's two steps. One of them sends from process P on node N to process P on node M. Okay, so you're communicating with a specific core on node N and node M, and then you do an exchange of information on node M to distribute. And so in a way, we're balancing across communicating cores how much information is being sent, and in total, for each one, we're reducing the amount of data. And so what happens on the left is the sparse matrix multiply for the setup phase. On the right is the sparse matrix vector multiply. And we notice that it's a mixed results. So in some cases, our former three-step approach was more expensive than the standard communication, and this two-step is better. That's for sparse matrix multiply. On the right, it seems that our three-step approach actually makes a lot of sense for the sparse matrix vector multiply, and so we should stick with that. But in general, how do we know this? Does it change for each problem? Does it change on size? Does it depend on which machine you're on? And so we have to go back to the models, and one of them is the max rate model, and we can extend this to be kind of a nodal max rate. And so we're adding a few pieces here. Here we have the injection bandwidth and the interprocess bandwidth, but then we're also going to distinguish between the maximum number of bytes injected by any interface and the maximum number of bytes communicated by any process. And if all of those are in balance, if we have the maximum number of bytes injected by any interface equal to the processors per node times the number of bytes communicated by any process, it falls back to the max rate model. And if we have a low number of processing cores per node, it backs out to the postal model. So we can extend this then, this nodal max rate model, then to the three cases. We have standard, and we have two-step, and we have three-step. And the only thing that changes is that we use that nodal max rate model plus the on-node postal model, And that's what each one of the three things looks like. So you can see it up here. This one, the standard, just looks like the standard max rate. Then we have an on-node penalty term, and then we have two of them for the three-step, one for the gather, one for the scatter. Okay. All right, let's see what the models show then. So we take those three models, and in the algorithm, we just time them. We time them a couple of times, and whichever one does best, we pick that for our communication routine and use that in our method. So level 4, we ran a bunch of times, and we're picking the green one, the three-step in this case. On level 2, ran it a few times, and in each one of this is probably one batch, and this is another batch. On that case, the two-step came up as the method that we should use. In other cases, on the fine level, standard communication does just fine. It doesn't make sense to pay for the overhead of doing a bunch of on-node work when everything is almost on-node anyway. Remember, we had that nice tight matrix on the fine level. And the results are good, right? We can take, here the blue line is our implementation of AMG, and just so that we're had a baseline. We also compared with the same hierarchy with Hyper, and we can reduce the number of, the amount of time in that phase. Okay. All right, so going back here, I kind of skipped two parts before. We have an all reduce in here that should not be ignored. And so far, I've been talking all about point-to-point communication. I think it's a natural question whether we can think about some of the same types of traffic mitigation strategies instead of applying it to our point-to-point, applying it to some collectives. And so this is some recent work that we've looked at, trying to look at the cost of the inner product. So if we go back to this paper is really great. It's a very good resource for this this type of modeling and complexity counting. If we do an all reduce of size S bytes with P processors, we're going to have at minimum P-1 S flops. That means that we have P-1 S minimum flops over P per process, and we need to do 2 times that minimum bytes to communicate. And so our goal is to do a log P minimum messages to communicate. We're going to take and plug that all into some models at the end and see if we can get any wins on the collectives. All right, so here's what just some refresher reminders. Here we have 4 nodes with 4 processors each, and this one's one style of doing that inner product to reduce and broadcast. And one of the problems is that it has large communication requirements for what we should expect, and it has inactive processors out of it. So there's also recursive doubling. I showed you the picture of the communication pattern between different processors at the beginning. This one does much better, has log P messages and log and internode messages. But it does have duplicate messages between nodes. And now we've seen that before in the sparse matrix vector multiply, that this is a great way to do it, but if we're communicating duplicate messages between nodes, there's an opportunity there. There's also a cost, and then the balance is going to be whether we can outweigh the cost of trying to rearrange off-node communication with the benefit of sending fewer messages in this collective. And then there's also the SMP approach, and this is the one that we looked at in MPitch, where you reduce to a master process in each node, you reduce among all nodes together, and then broadcast the results on each node. It does leave idle processes in this case, and we're going to compare against both of those. The approach that we took is probably most easily highlighted in the for case, and then it becomes messier but doable when there's more processors and more nodes. But it looks much like the SMP approach, and it looks like the SMP approach, but we're going to try to use all processors per node to communicate information between other nodes. And so you can see we do a reduction among all processors local to a node, and then each local process reduces with a particular separate node, and then we start doing the collection again. And so this is going to take a couple of steps. If we have 16 nodes with 16 processes, it takes one step to do this. If we had 4,096 nodes with 16 processes, it's going to take multiple steps for each one of the groups of nodes to have the same amount of information from every other one. And so what happens when you extend this is that we organize them into subgroups of nodes, and we have to do an exchange. Kind of going over this part quick, but in this case, we would have a unique person for P7 to talk to. That would be P52, and we would do that exchange. All right, back to the models then. So we're going to take the same model that we had before. It looks like a local alpha beta model. It looks like a max rate off-node model, and then plus a computation term. And then we're going to take all of those numbers of messages off-node and on-node and plug them into this for the three different routines: the recursive doubling, the SMP, and the node-aware approach. And the model says, well, it looks like you should be able to reduce the model time, or the compute time there. And in practice, we saw that. So here we take a reduction of 8 bytes and increase the number of processes, and we can see that the node-aware approach does okay, and we get some good speed up with that. We can do the same thing with 32,000 processes and increase the number of bytes, and we see that it works well until we get to that large byte size, and that's kind of to be expected. One notable comment about these plots: we implemented this on top of the MPI iSend and iReceive. We have some comparisons with the actual MPitch implementation in the paper, but getting these algorithms closer to the implementation will be necessary to have kind of optimal times. All right, some conclusions then. Behavior of irregular communication can be irregular, and that's not a surprise, but it also presents an opportunity when you can manage the communication between nodes. Models are helpful in identifying both what we should do in the algorithm and what we should be doing to communicate, or what's limiting our performance. And of course, there's a lot of places where this needs work. We're working on developing an iSend and iReceive drop-in replacement so that we don't have to build a whole new communicator every time that we want to do this for a new problem. We've kind of sketched that out in a package called Streamline. There's some extensions that should be and can be done in heterogeneous systems, and memory hierarchies of different types of compute units. Both of these talks, since we're on Saturday, happened before us, but they're excellent and starting to make progress in those directions. And then ultimately, we would need a coupled approach. So models are really helpful in terms of understanding what to do for a particular problem. Model-driven algorithms and model-driven decisions and removing data and layouts and partitions and communication traffic all needs to go together. So here's where you can find more. And thanks again to the organizing committee for a great conference and for having me here. Yes.
Hi, great talk. My name is Kostas Bekas.
Yes.
How would the models behave in a situation where the network is multi-used?
When the network is what?
Yeah, I mean, imagine that you don't have a dedicated HPC partition anymore.
Yeah.
But you have a multi-programming environment with many different applications happening. Have cloud in mind, for instance.
Yeah, this is a fantastic question, and I think it's this is a really relevant one. I think even on a quiet network and a dedicated machine, you have trouble understanding all of the components to some of the communication. I think the short answer is I don't know. I think there's probably a next stage of modeling where we need to do some sensitivity analysis or something like that. I think that's a fabulous critique, though.
So I really like the work. Have you tried to take the all reduce back, and especially the smaller ones, and put them into an application and see if it benefits things? Because we've had trouble with small all reduces not being faster, but not helping any applications because of a variety of factors.
Yeah, that's probably going to be one of the next steps when we get the implementation closer to MPitch. So I think the plan is to see if we can get some of these implemented along with the recursive doubling one, and then we can start looking at applications. Good point.
Sounds good.
Hello, thanks for your talk. Have you thought of node-aware one-sided communications?
Oh, yeah. Yeah. We haven't done anything with it, though. I think there's that would be kind of a unique opportunity for some of this too. So no, we haven't done much with it, but I think that's a fantastic comment.
One question that came to my mind, you have worked a lot on geometric multigrid methods as well. So do these methods also suffer that much from what you observed in AMG?
Yeah, so one of the issues with geometric multigrid is that it's structured. That's a challenge because you need to do stuff very systematically and where all of the data goes. With David Moulton and Andrew Reisner, we did some work on redistributing information at coarse levels, and so did Hormost in an algebraic setting. And there it uses predictive modeling in the same way. So it takes an alpha beta model and it says, out of all the different ways to coarsen, what's the best one? And then it selects those kind of on the fly. I think in general, extending that model is going to be important, but that's kind of the progress we've made in that area. Good question.
Further questions? And let's thank Luke again.
Thank you.